Good morning. My name is Alejandro Jefté Alvarado, a student from Universidad Autónoma de Baja California, in the Facultad de Arquitectura y Diseño. At the moment, I am in the 7th semester of the career of architecture, and currently I am in an internship in Burgos, Spain, for 6 months. I have the honor to present the article Analysis and Comparison of Thermal Lag in Material of Finishes Type in Dwellings of Social Interest in the City of Mexicali, Baja California, which I realized with the architect Luisa Paola MURGUIA Tostado, the architect Francisco Gibranny CURIEL SÁNCHEZ, and Dr. Ixchel Astrid CAMACHO IXTA as our coordinator. In the line of investigation, 7th area, Mechanical Engineering and Thermal Flow. Welcome. Now, going with the introduction, derivative of several human activities, the concentrations of greenhouse gases have increased. According to a recent study, CO2 is one of the gases that has increased the most since the Industrial Revolution, principally due to fuel burning, contributing to the development of global warming and temperature increase. Otherwise, if the climate concept is considered, the environmental conditions, the basic need that is architecture, and in punctual manner the dwelling, it is characterized for being the main instrument to satisfy thermal comfort to whoever habits it. This does not only create harm from its realization, if not in its use and maintenance, that is to say, to supply the basic needs like the use and waste of electric energy, natural or LP gases, potable water, drainage, inter alia. In addition, several investigations affirm that dwellings constructing methods lack of thermal benefits for the users, despite that human beings are distinguished for having homothermic qualities. That is to say, they have the ability to keep their internal temperatures independent to any climatic conditions. Nevertheless, exists a constant thermal change between man and the environment. That is the reason there is a need to search for efficient alternatives that contribute to a thermal reinforcement of house facades. There are a great number of researches that study walls and roof materials. All of them keep a relation with the thermal comfort and conclude that the application of thermal insulators or thermal retardants in facades are one of the most efficient alternatives in reducing the thermal transmittance. Consequently, these insulators became the intermediates of the energetic exchanges between two complex environments, the inside and the outside. With the intention to solve the presented problematic, several companies continue a constant innovation and development of materials and construction systems committed to the environment, thus to increase the user's life qualities. Nevertheless, it is required to prove and analyze that the materials fulfill the necessary characteristics to provide a thermal support, in this case, the envelope. Thus, the objective of the present investigation was to analyze the thermal behavior of a material which pledges efficient thermal lag qualities in comparison with traditional plastering. The object of the study was the city of Mexicali, Baja California, Mexico, where two cases of study were compared under traditional construction systems of the region, as it is the concrete block. Nonetheless, one of them bears the thermal retardant called thermal rock. Now we can proceed with the methodology. This research is developed following a thermal logger monitoring method. We consider other similar papers as references to elaborate the methodology of this article, which it is described in the following chapters. It is truly important to point out that we consulted the following standards: ISO 9869-1-2014, Thermal Insulation Building Elements in situ, Measurement of Thermal Resistance and Thermal Transmittance, to warranty the log's level of confidence, and the standard ASTM C16897, standard terminology relating to thermal insulating materials, as guide to determine proper nomenclatures. Two kinds of temperature loggers were used in this research. For environment, temperature, we use a thermal stress sensor RC51H model that has an EN12830 certificate, CE-ROHS. For surface temperature, we use a 4-channel logger thermometer. Both sensors were programmed on fields. This study was realized in Mexicali, Baja California, Mexico. This city has a BW climate, Köppen Garcia categorized, which indicates that it's an arid, dry climate. It has rainy winters and an annual very extreme temperature oscillation. The annual average temperature is 22.4 degrees Celsius. The warmest season is from June to September, whose average temperature is 33.1 degrees Celsius, and it can get to a maximum of 42.2 degrees Celsius. Meanwhile, the coldest seasons correspond from December to January. In this period, the monthly average temperature is 12.4 degrees Celsius. The precipitation is poor, 75 millimeters in a year. During summer, there are plenty of insolation hours, from 2,400 up to 2,500 hours per year with a uniform distribution. Wind velocity can reach 100 kilometers per hour. The monitoring was done in 2 houses located in Ángeles de Puebla, a division placed in the southeast side of Mexicali, Baja California. The following analysis correspond to the thermal lag comparative, exterior and interior of the same orientations on both dwellings. In the transition period, the date of November 15th of 2021 reached the highest temperature in the environment, which was 33.8 degrees Celsius. Meanwhile, the lowest temperature was 10.8 degrees Celsius, with an oscillation of 28 degrees Celsius. Now, the month of January was classified as the cold period due to its low temperatures, where the critical date was January 4th, 2022, with the highest temperature of 18.3 degrees Celsius and the lowest of minus 0.5 degrees Celsius, with a thermal difference of 18.8 degrees Celsius. First, we're going with the results on roofs. The first graphic corresponds to the critical date on November 15, 2021. So, the following graphic shows the exterior side of case 1, called C1REXT, which increases 10.8 degrees Celsius, and its oscillation is 38.8 degrees Celsius. The heat earning is reflected in the interior side, named C1RINT, with a thermal lag of 2 hours that decreased to 28.2 degrees Celsius, with a difference of 8.9 degrees Celsius that reached to 19.3 degrees Celsius according to the environment. In case 2, the same heat gain phenomenon occurs. In the exterior side, C2REXT reach a maximum temperature of 42.8 degrees Celsius and a minimum temperature of 8.2 degrees Celsius, which means an oscillation of 34.6 degrees Celsius. Now, on the cold period, which was on January 4th, 2022, the roof of case 1, C1REXT, presents a maximum temperature of 29.7 degrees Celsius and a lowest of minus 4.6 degrees Celsius, which results in an oscillation of 34.3 degrees Celsius in a 7-hour lapse. Meanwhile, on the interior side, C1RINT, the highest temperature was 16.8 degrees Celsius and a lowest of 8.3 degrees Celsius, which resulted in a difference of 8.5 degrees Celsius also in 7 hours. In case 2, the exterior side, C2REXT, The highest temperature was 27.1 degrees Celsius and the lowest of minus 3.5 degrees Celsius. That represents a difference of 30.6 degrees Celsius in 6 hours. On the other side, its interior, C2RINT, reached a maximum of 21.3 degrees Celsius as the maximum temperature and 11.8 degrees Celsius as its minimum, which is an 9.5 degrees Celsius oscillation in an 8 hours time interval. Now the results of the West Wall. Transition period November 15, 2021. In case 1, C1WWEXT was the same temperature as in the environment, with an oscillation of 12.9 degrees Celsius. Meanwhile, the interior side, C1WWINT, the heat transfer is presented 2 hours later, decreases to 27.7 degrees Celsius, it is to say, it reduces 6.1 degrees Celsius, and the thermal oscillation is 7.1 degrees Celsius, which represents a more stable temperature than the exterior side by 5.8 degrees Celsius. In case 2, C2WWEXT, the maximum temperature was 32.4 degrees Celsius, with its oscillation of 15.1 degrees Celsius less than the environment. Likewise, in case 1, the thermal lag is reflected in the interior, C2WWINT, in 2 hours. It minimized to 32.4 degrees Celsius with an oscillation of 10.9 degrees Celsius. The thermal oscillation is more stable than the environment with 17.1 degrees Celsius. Now, the cold period, January 4th, 2022. In case 1, in the exterior, C1WWEXT, the highest temperature registered is 18.1 degrees Celsius, while the lowest was 12 degrees Celsius, which means an oscillation of 5 hours. On the other hand, the interior side, C1WWINT, presented a maximum temperature of 20.4 degrees Celsius and a minimum temperature of 10.7 degrees Celsius, with a thermal lag of 6 hours. Otherwise, on the exterior side of case 2, C2WWEXT, the maximum temperature reached 20.8 degrees Celsius, whereas the minimum temperature was 9.1 degrees Celsius, which means an oscillation of 11.1 degrees Celsius in an 8 hours interval. Meanwhile, the interior side, C2WWINT, obtained the highest temperature of 20.4 degrees Celsius and a lowest temperature that descended to 11 degrees Celsius. That represents an oscillation of 9.4 degrees Celsius with a thermal lag of 11 hours. Now the results on the east wall. In case 1 in the exterior, C1WEXT, reached the maximum temperature at the same time as the exterior, 50.3 degrees Celsius, and its minimum temperature was 15.3 degrees Celsius, a difference of 35 degrees Celsius, less stable than the environment, while the interior, C1WEINT, the highest temperature was presented 3 hours later, and it decreased to 31.5 degrees Celsius, and the thermal oscillation is more stable, with 12.4 degrees Celsius. In case 2, the results are similar. The exterior side, C2WEXT, has a heat gain that got up to 44.5 degrees Celsius, a 27.6 oscillation, and a thermal lag of 5 hours. The maximum temperature in the interior, C2WEINT, was 37.3 degrees Celsius, a resultant oscillation of 16.6 degrees Celsius. Now, the cold period, its critical date, January 4th, 2022, the exterior side, C1WEEXT, the highest temperature was 57.8 degrees Celsius, and the lowest minimized to 28.8 degrees Celsius. That represents a difference of 29 degrees Celsius in an 8 hours time lapse. On the other hand, on the interior side, C1WEINT, the maximum temperature reached 38.2 degrees Celsius, while the minimum was 26.6 degrees Celsius, which is an 11.6 degrees Celsius oscillation in an interval of 12 hours. Case 2, in its exterior side, C2WEEXT, reached the highest temperature of 31.5 degrees Celsius and a lowest registered temperature of 5.3 degrees Celsius with a thermal lag of 4 hours. The interior side, C2WEINT, registered the maximum temperature of 24.8 degrees Celsius. In contrast, its minimum temperature was 9.2 degrees Celsius in an 8 hours time lapse. Now the results on the south wall. Transition period, critical date November 15th, 2021. The final comparisons show that in the exterior side of the south orientation, C1WSINT, the highest temperature was 50.1 degrees Celsius, with a 36.8 degrees Celsius oscillation. On the other hand, the interior side, C1WSINT, its maximum temperature reached 46.4 degrees Celsius, presented in a thermal lag of 2 hours and an oscillation of 26.6 degrees Celsius, which is more stable than the environment. Case 2 registered in its exterior side, C2WSEXT, 55.7 degrees Celsius as its maximum temperature. It represents a heat gain of 21.9 degrees Celsius and a minimum temperature of 16 degrees Celsius, which resulted in a 39.7 degrees Celsius oscillation. Meanwhile, the interior side, C2WSINT, the highest temperature was 43.5 degrees Celsius, more than the environment for 9.7 degrees Celsius, with a 23 degrees Celsius oscillation, more stable than its exterior side and environment. To finalize, we can observe the temperature behavior on the south wall. On the cold period, which was January 4th, 2022, where it indicates that the variables stay superior compared to the exterior. The exterior side, C1WSEXT, the highest temperature was 46.9 degrees Celsius, which occurs at the same time as in the environment. The lowest temperature was 27.7 degrees Celsius, that in a similar way happened at the same hour as in the environment, which indicated an oscillation of 19.2 degrees Celsius, while in the interior side, C1WSINT, the maximum temperature was 41.1 degrees Celsius, which happened with a thermal lag of 4 hours. On the other hand, the minimum temperature was 25.6 degrees Celsius in an interval of 8 hours, where the thermal oscillation was 15.5 degrees Celsius. Case 2, exterior side, C2WSEXT, reached the maximum temperature of 42.9 degrees Celsius, with a 38.3 degrees oscillation, while the interior, C2WXINT, presented a highest temperature of 31.1 degrees Celsius, with a thermal lag of 4 hours, and a lowest temperature of 8.9 degrees Celsius, which is a difference of 22.2 degrees Celsius. This indicates the instability of the environment for 3.4 degrees Celsius. Now, we can continue with the conclusions. So, during this period, it was observed a decrease in the thermal oscillation between the surfaces of both cases of study, thus a clear tendency to a measured stability in the housing, where it was applied an extra covering, which was a research objective. It can be concluded that the use of finished material studied in this paper in construction systems helps the thermal lag and the reduction of superficial temperature. This is reflected in the diminution of thermal amplitude. This allows the possibility to reduce earnings and heat loss inside the habitable space and facility in the control of environmental temperature. Here is the first part of our references, and here is the second part. We express our sincere gratitude to Thermorack for all the facilities granted throughout the process of this research. With nothing more to say, we are grateful for your time. On behalf of the team made up by the architect Luisa Paola TOSTADO, the architect Francisco Gibranny CURIEL SÁNCHEZ, Dr. Ixchel Astrid CAMACHO IXTA, and me, Alejandro Jefté AGUILAR ALVARADO. Thank you.